Hello, and welcome to Lecture 9 of AMAT502 at UAlbany. Today we're going to continue our study of object-oriented programming as we move on to some of the built-in packages offered by the Python ecosystem, namely matplotlib. We're going to look at an extended example of object-oriented programming applied to the study of mortgages. Some of you might not be thinking about having a mortgage, but this is important financial advice to learn now, and also will inform your understanding of how much you need to save for retirement, which we'll do in class exercises. So the topics for today are going to be, first, highlighting the importance of studying mortgages by looking at what was one of the primary causes of the Great Recession in 2008. We're going to go ahead and derive some of the formulas for what's called an amortization schedule, which is how you pay off your mortgage. And that's going to help us understand some of the things that went wrong during the 2008 crisis. And then finally, we're going to depart from the prescription offered by Guttag, where he uses pyplot to use matplotlib, which is the standard package for plotting in Python. So let's get started. So I encourage you to take a little break to go ahead and watch some of these clips from YouTube. But to highlight it in broad strokes, before the current crisis in 2020, one of the most severe economic downturns occurred in 2008 due to a collapse in what was called the housing bubble. This really exposed some serious structural flaws in our economy. And if you want a sense of comparing how bad this, how bad the 2008 crisis was compared to the COVID crisis, I encourage you to look at this article from the Atlantic Council, where you can see here the comparison of the downturn caused by the 2008 crisis, a pretty large relative drop from this position here compared to what's happening now in 2020. Additionally, it might be fun for you to go ahead and take a break and watch some of this YouTube summary of The Big Short, which is a movie that came out not too long ago to explain what happened.
Listen, open the darn Fed window. He has no idea how bad it is out there. He has no idea. He has no idea. I have talked to the heads of almost every single one of these firms in the last 72 hours, and he has no idea what it's like out there. None! And Bill Poole has no idea what it's like out there. My people have been in this game for 25 years, and they are losing their jobs, and these firms are going to go out of business, and he's nuts. They're nuts. They know nothing.
You may be old enough to remember exactly how bad fiscal year 2008 was for America. If so, you were probably one of 8 million people that lost their jobs as a result. But if you're like me and you were too young at the time to understand what was going on, allow me to explain exactly what happened and why. A little Finance 101 to get us started.
So I'm going to encourage you to keep watching this video. But the context here is that just as things are very bad right now, things were also really bad about 12 years ago. And the long-term economic consequences meant that a lot of people who developed a lot of their wealth because of the equity in their house suddenly lost that equity and had to default on their mortgages and often ended up going bankrupt. So this was a very serious structural problem, and one which wasn't necessarily addressed by helping everyday people. In broad strokes, what essentially happened here was that people had figured out certain mechanisms to bet on people paying off their mortgages. And even when some of the investments looked really bad, they were able to somehow diversify portfolios to make it look like it was actually a good investment. And moreover, the bank would often buy bonds that were meant to insure their own investments. So they ended up in this sort of circle where they could never lose money, or at least never lose money, assuming a certain percentage of mortgages didn't default. But that's exactly what happened in 2008. Roughly over 8% of mortgages were defaulted upon, and suddenly banks didn't have any money, and the lifeblood that drove the US economy, and hence the world economy, collapsed. So let's go ahead and try to understand some of what happened and why suddenly people weren't able to pay off their mortgages. But to understand that, we first need to understand some of the typical offerings there are for mortgages. The gold standard nowadays is a 30-year mortgage. Back in the 1910s or 20s, we didn't even really have mortgages that lasted longer than 5 years. It was a new concept introduced in part to help Americans build wealth. So the typical package that people buy nowadays is a fixed rate 30-year mortgage. Of course, you can also get a fixed rate 15-year mortgage, which that essentially means you pay off the entire amount you borrow to buy your house in 15 years rather than 30 years. We'll see why that makes an important difference soon. There are other options which exist in purchasing a mortgage. Sometimes you can get a lower interest rate by purchasing what's called points. Points are essentially just saying that you'll pay even more down in order to establish a down payment. Again, this is the hardest thing that keeps people from buying houses, is that you need to have a large amount of capital, ideally 20% of your home's value that you can put up front. But in reality, you can actually get by with closer to 5%. But sometimes that comes at a higher interest rate. And this is why sometimes people are asking you to access lower interest rates by putting more down. And perhaps one of the most nefarious mechanisms is one where you start off with a teaser rate. This is kind of like a credit card where they promise 0% APR, so 0% interest for a certain period of time, but then immediately switches over to incredibly high percentage, which suddenly makes you having to pay hundreds if not thousands of dollars in interest, unrelated to the amount of money you borrowed to make your purchase. So to really understand what goes on with mortgages and why the mathematics behind mortgages is often hard for a lot of people to understand, is you have to look at the miracle of compound interest. So it's often said that in 1785, a French mathematician by the name of Charles Joseph Mathon de la Cour wrote a parody of Ben Franklin's Poor Richard's Almanac. Of course, Ben Franklin was one of the founding fathers of this country, and also a scientist who understood a lot of things about math and science. But either way, de la Cour decided he would mock the unbearable spirit of American optimism represented by Franklin. And so instead of doing Ben Franklin's Poor Richard's Almanac, he created a fictionalized Fortunate Richard. And in this thought experiment, he leaves a small amount of money that is then used to be compounded with collected interest over 500 years. Apparently, Franklin, even though he was nearly 80 at the time, became aware of de la Cour's parody. And he wrote back to de la Cour and said, he's like, you know, that's a great idea. Actually, compound interest will earn a lot of money. So then he decided to leave £1,000 to both Boston and Philadelphia, two of his favorite cities in America. And then he made it part of the rules that they couldn't retrieve the funds until I had earned interest for 200 years. £1,000 with 200 years of compound interest ends up earning quite a lot of money. So both Philadelphia and Boston ended up with millions of dollars to invest on things that Ben Franklin would have liked to see. All right, so let's try to understand exactly how compound interest works. And to do this, I'm gonna go ahead and expand this so we can see the equations here a little bit better. All right, so the basic idea behind compound interest is that, like with anything where you borrow, you loan someone money with the expectation that they're gonna pay it back plus with a little extra interest. Essentially, you wanna view it as a convenience fee for giving someone money that you're not gonna have for a certain period of time. So let's say that that percentage that people have to pay back is R, so R%. The way compound interest works is that if someone loans you some original amount, we call that the principal. And let's say you pay it back immediately, then there's no reason for you to incur any interest on that charge. But suppose you take a year to pay back the money. The agreement that you make between whoever's loaning the money and you is that you'll pay back the original principal plus some R%. So that this one represents 100% of the amount you loaned out, plus an additional R% in interest. Now, let's suppose you don't get back to the payment right away. And so instead you incur 2 years of interest. So what that means is that you have all the amount plus interest that you're supposed to pay back in the first year. And then suddenly that whole quantity is again multiplied by 1 plus R, reflecting the fact that you have to pay back 100% of the loan amount, P, plus that interest. And now you pay in another R% on top of that combined amount. Mathematically, that leads to P times 1 plus R squared. And so if you make no payments over n pay periods, you think of this as in years or in months, depending on whether or not R represents yearly interest or monthly interest, then this is the amount that you end up owing after n repayment periods if you don't make any repayments. You'll notice that this grows exponentially. And that's really the miracle of compound interest, is that small amount of money grows exponentially with time. All right, so just as a quick conceptual question, suppose you loan out two different amounts of money, P and P prime. You want to think of this as, you know what, if I'm borrowing 5,000, maybe I might as well borrow 10,000. Let's call that difference between 10,000 and 5,000 delta. I want you to think about, how does the difference in the amount you need to pay back grow between each of these? Is it double? Let's say you took out twice the amount, 10,000 rather than 5,000. What's the difference after, say, 10 years where you have to pay 5% interest every year? Go ahead and try to do that calculation and see what you get. All right, so let's move on. So the whole point around a mortgage calculation is that you don't want to end up having an unbounded amount of debt. That means you'll never go out of debt. You'll die with debt. And that's something we ideally don't want to have. So we're going to instead make some monthly payment. And we want to make this monthly payment under the stipulations we already outlined with regards to a mortgage, meaning that you pay off the entire amount that you owe the bank within 30 years or 15 years. So how do we figure out how much do you have to pay so that even though your principal is accruing compound interest, that over that period of time, you can actually pay it off? This is a relatively complex calculation. And I'd say that most people who take out mortgages don't actually understand how this calculation is derived. So let's go ahead and try to derive it for ourselves. Again, I'm assuming everyone here has done up through at least calculus. So they're familiar with exponentials and the like. Honestly, anyone with pre-calc can understand this calculation. It just requires a little understanding of series, which we'll go over. All right. So let's go through our setup here. Instead of accruing pure compound interest, we're going to subtract a monthly payment M. This is going to be your mortgage payment. That allows you to reduce the amount of principal and interest, because again, we're earning interest on the principal that would accrue. All right, so let's see how this works step by step. So at time 0, you take out a loan of principal amount P0. So that's the amount that you owe right when you first take out the loan to buy your house. So after 1 month, and here we're going to assume that R is now monthly, your monthly percentage. So you take your annual percentage, let's say it's 4 or 5%, divide by 12. Reality nowadays, things are even lower, like 3.5%. But either way, let's say it's 5%. You divide by 12. That's going to be R. So if you make no payments and you just look at what happens over that month, the bank suddenly has accrued interest on your loan at P0, and that amount is P0 times R. All right, so now at the end of this month, we're going to make our first monthly payment. So we want to see how much the principal has changed. Again, that's the amount we've actually loaned out. So let's see what that is. So the principal after 1 month is P1. That's just our notation for it. What is P1? What is it equal to? Well, it's the amount that we initially loaned out, P0, minus our monthly payment. And of course, I have this minus sign inside of here, but if we think about minus goes against minus, makes plus, plus the interest accrued on the total loan amount. So if we go ahead and redistribute that, as I've indicated, we're gonna have P0 times 1 plus R minus M. All right, so all that is, it shows exactly how much your principal has grown minus whatever this monthly payment M is. So I just want you to notice something, that if M is not greater than P0 over R, you'll never pay down the loan. Why? Well, if M is smaller than P0 times R, then M minus P0 R is negative, which means that we have a negative times a negative is a positive. And so we've actually increased the amount that we owe. The goal is for that to actually decrease with each payment. So we need to assume that M, our monthly payment, is greater than our initial principal times our monthly percent. That's the only way we'll ever pay down our loan. Again, banks would be fine with this because they would essentially get a paycheck for the rest of your life without having to do anything, just because they had the capital to loan the money out to you and you didn't. And this is where you'd be left perpetually in debt. Luckily, we have federal laws which say that people can't be perpetually in debt. All right, so let's continue this calculation. And I know this is going to look like a mouthful. All right, so now let's see what happens after our second month. So notice we've kind of got a recursive formula here. Instead of using P0, we can use P1. So we have P1, that's the amount of principal that we have after our first month. Again, we just derived that in the last slide. And we want to subtract our monthly payment, where we've then also subtracted off the amount of interest accrued on P1. That's the amount we had after 1 month. So again, we can rearrange this. So it's P1 times 1 plus R minus M. So this is exactly the expression we had on the last slide, except we had P0, and that was the definition for P1. So in general, you can always write PK is equal to PK minus 1 times 1 plus R minus the monthly payment. All right, well, let's go ahead and unpack. What was P1 again? Again, we derived that. It was P0 times 1 plus R minus M. So this expression here, that's exactly what P1 was. And notice we've got this 1 plus R multiplying by it. Well, there's another 1 plus R factor here. So if we go ahead and distribute and collect like terms, we get that P2 is equal to P0 times 1 plus R squared minus M times 1 plus R minus M. So M, again, is your monthly payment. This actually kind of makes sense. So just to step back for a second, if we made no payments, meaning M was equal to 0, then after 2 payment periods, 2 months, our principal would have grown by 1 plus R squared. Again, that's quote unquote miracle of compound interest. In this case, it's the miracle of debt. Okay, but remember, we made a payment of amount M. So we get to actually subtract off the amount of interest and principal that would have accrued on M by making that first payment in that month. And then we also get to subtract off the payment we just made. So you kind of get to take advantage of this sort of negative interest. You're saving yourself from having compound interest accrued on the payment you made 1 month ago. Notice that that's 1 plus R to the 1. I leave it to you to convince yourself that after K months, your principal would be PK, which is equal to P0 times 1 plus R to the K. Again, that's the principal that would have accrued if you made no payments, meaning M is 0. And then you get to save yourself the interest on M after K minus 1 months. Also, and that was because you made a payment of M in that first month. And then you made a payment in the second month and you saved 1 plus R times K minus 2 interest off of that. So all these things subtract off. And again, you get to collect like terms until you arrive at the following expression, which is that P0 times 1 plus R to the K, that's what would have accrued if you made no payment, minus this partial sum, or it's a sum of terms of 1 plus R to the J from J equals 0 to K minus 1. Now this looks like something that's called a geometric series. And luckily we have formulas to provide a closed form formula for this. Let's see how that works. So just as a reminder, when you look at the sum of an infinite geometric series, so that means where you go 1 plus x squared plus x cubed, you keep doing x to the 4th, x to the 5th, go on x to a billion, plus so on and so on. It goes on forever. You write that in sigma notation as sum of terms x to the j from j equals 0 to infinity. That all equals 1 over 1 minus x. So I encourage you to try to remember how to derive that. Of course, we can also do it in class. All right, so let's go ahead and leverage this formula to come up with a formula for a geometric progression where we sum 1 plus x squared, but we stop at x to the k. What does that equal to? Well, let's figure it out. So I see now, so I'm going to have to pop out of my slides temporarily, just because this expression stretches so far. So remember, if I have 1 plus x squared all the way up to xk minus 1, and then I have xk plus 1 on through infinity, I can rewrite that and I can pull out an x to the k from this term and all higher terms. So that means I've got the partial sum from 1 up to xk minus 1 plus x to the k times 1 plus x squared plus x cubed on to infinity. All right, now we have a closed form formula for this infinite sum. It's right up here. It's 1 over 1 minus x. So I can think of this infinite series as also 1 plus x squared plus x cubed up to xk minus 1 plus x to the k, because that's we factor out this term, times again the whole infinite series. So you kind of see this self-similar copy of the expression inside of itself. So you have x to the k over 1 minus x, because that's the sum of an infinite geometric series. And we know that all of that actually still equals 1 over 1 minus x to the k. All right, so now we're ready to finish the calculation. So just try to make that a little sharper. So by rearranging terms, we end up getting that 1 plus x up to xk minus 1 is equal to, bring this over to the right-hand side, they have a common denominator, and so now we have 1 over 1 minus x to the k. That's what happens when we combine the numerators, and that's exactly the expression here. So here's an important formula. The sum of the first k terms, where you use, just like Python, start with counting with 0, and you end with k minus 1, where k is the length of this sum, is equal to 1 minus x to the k over 1 minus x. All right, that's going to be really important. So let's try to remember that. Sum of the first k terms in geometric series is 1 minus x to the k, all divided by 1 minus x. All right, so what is x in our setting with mortgages? Well, it's 1 plus r. We have to pay back everything we borrowed plus r%. All right, so the sum from j equals 0 to k minus 1 of 1 plus r, you can plug in that formula. Again, this is our x to the k term. It's 1 plus r to the k minus 1. But in the denominator, we had 1 minus x. And 1 minus x, or where x is 1 plus r, well, the 1's cancel. And so that just leaves us with r here in the denominator. So we now have this partial sum of the amount of interest saved from each of our mortgage payments. So we can plug that all in. And now let's use the fact that we've agreed with the bank that after n months, so for a 30-year mortgage, that's 360 months, we have to have paid off our loan. We then have the equation that Pn, where n is 360 in this case, has to equal 0. And so this gives us another relation so that we can actually solve for m. So how do we do that? Well, we can know this is equal. We can bring m times 1 plus r to the n minus 1 over the left-hand side where the 0 is. And now we can just go ahead and flip it and multiply by p0 times 1 plus r to the n. And when you do that, flip and multiply, you can see the r multiplies against p0. That gives us this numerator here. And then 1 plus r to the n minus 1, that becomes our numerator. And so now we've actually derived the formula for what your monthly payment is. If you take out some initial principal loan P0, which is the amount your house costs, plus r%, where you've agreed to pay off the loan after n months. We're going to use this to help experiment to see with how our payments go over the course of a loan for a house. This is also going to be a really important formula for figuring out how much you need to save to retire, because retirement is essentially like a reverse mortgage, where if you put in $10,000 now, you'll accrue some interest based on that deposit from now until retirement. But then if you put in $10,000 the next year, you'll only save that amount of money, you only earn interest on that amount of money from years to your retirement -1. And if you put in, a few $1,000s in 3 years, then you're only going to earn that period up to your retirement minus that 3 years. So retirement actually looks a lot like a reverse mortgage. Okay, so all this was to allow us to explain how to come up with this find payment function, which we've used to implement in our mortgage class. All right, so how does this work? So we define a function called find payment, where we have our loan amount, that's P0, R, which is our rate of interest, and M, which is going to be the total loan period. That's the number of months. M is for months. And so we've essentially, again, you always want to use return instead of print. So you return the formula we just derived. So it's P0, it's loan, times R, times 1 plus R raised to the nth power, divided by 1 plus R raised to the nth power minus 1. All right, so we're going to use this now in our mortgage class. So again, everything in Python is an object at runtime. So that means that mortgage gets to inherit whatever attributes object has, where object is sort of the overarching class that contains all other Python classes. We're going to have an init function, and our init method, I should say. So this means that when we take out a mortgage, and we're going to call it some variable, which gets bound to self, we then need to give the important information of a mortgage, which is our loan amount, the annual rate, and the number of months. So again, this is then used to populate all these attributes of our mortgage class. So self.rate is going to be annual rate divided by 12. That's going to be our R, called up here in find payment. And then what we're going to do is we've got our months. We're going to initialize a list where we look at the amount we've actually paid into our mortgage. And we start with initially 0. But then we also need to look at the amount owed. And so when we first take out that big loan in order to buy a house, we've made no payments. The first entry in our list is going to be the total loan amount. All right, so let's go ahead and figure out how the rest of this works. So we call our find payment function, which is defined outside of our class, although we could have probably done it inside the class. But right now we want to make sure we can access it. All right, so remember, we've got a mortgage object. Some people only have one, some people have multiple mortgages. So let's imagine, what are the operations you can perform on a mortgage? One thing you can certainly do is you can make a payment. It's the thing we don't like to do, but it's the thing we have to do. So what that does, the inner workings, if you dive down into how this is implemented, is it takes our lists of paid amounts and it appends the amount we paid, which we're assuming is the amount set by this mortgage calculation we just did, what capital M is. That's our monthly payment. And then we figure out how much we've reduced. So what we do is we take self.payment. So again, that was our monthly payment, minus our self.owed, and it looks at the last entry. That's what that -1 does. And then it takes that self rate. So meaning it's that monthly interest earned on there. Again, essentially here what's happening is we're rederiving the formula. We have our M minus the principal from the last month with its accrued interest. That's exactly this. So this is the amount that was at the last month. All right. And so then we go on to see how much is owed. Well, we look at the last entry of owed, and then we subtract the reduction. So again, if you look carefully, this is exactly this formula back here. So just remember, so we have self-owed minus reduction, where reduction is this minus that. All right, let's try to click back a few slides and see where that works. Right, so this was our monthly payment minus the last entry here, and the first one is P0 times that rate, which then when you see redistribute it, looks like this, which is the amount that accrued on your loan minus your monthly payment. Or again, when we did it for P1, P1 is our last entry. So we had our monthly payment, our self.payment minus that. And then that was then taken away from the amount owed. All right, let's see if we can remember that. Yeah, self-owed minus reduction. Reduction is this. That's exactly that formula. P1 minus this reduction, which would have been P0 times the self rate. All right, and then we get to use a built-in function here. So this is a self.paid. It's going to sum up all the entries in this list. So you're going to see how much you pay over the course of your loan. That's going to be done by this get total paid attribute on your mortgage. And of course, when we want to print our mortgage, we're going to return this legend. Right now, we just populate it with none. But as we go on, we're going to add things to this. All right, so let me go ahead and hit Shift Enter so this is brought into memory. All right, good. So we're going to have some other types of mortgages, the ones which I just introduced at the start of the lecture. So we have our fixed mortgage, and we're going to express that as a subclass of our mortgage class. So again, the fundamental workings of any mortgage were just outlined in this previous mortgage class, which was a subclass of object, where you can make a payment, get total paid, and you can print it using the string method. But now we're going to define 3 different subclasses. We've got our fixed type of mortgage, we have a fixed with points, and then we have a 2-rate mortgage. And this is one where you start off with some teaser rate, and then as time goes on, it switches and jacks up to a higher rate. And so these are all done by modifying how we deal with the self.legend. But you'll notice that in all these cases, when we have our init method inside of the subclass, we're just going to essentially use the same init method from its superclass, mortgage, and then we're just going to modify the legend. The fixed with points, though, has other attributes that are not defined for a general mortgage. It's only defined for mortgages with points. And that's where we bring in the self.points attribute. And now self.paid also needs to be modified slightly because, again, part of the agreement with a mortgage with points is you pay a little extra down. Okay. So I'm going to leave it to you to try to understand some of the inner workings here. And we'll just move on. Okay, so once we've specified these 3 different classes of mortgages, we want to go ahead and compare them. And what are our arguments for the compare mortgages function? Well, we're going to look at the loan amount, the number of years. We can do a fixed rate with points, a points rate, and then we can also do a variable rate 1, variable rate 2 with a variable number of months. So this is essentially tells you, suppose you want to take out a 2-rate mortgage with that same amount, where you then have a certain rate, variable rate 2 for a certain number of months, and then you have variable rate 1 for some other set period of time. This is exactly like with a credit card. It says like 0% down for the first 36 months. All right, so all this function does is it then calls a for loop, uses our total months period. And again, total months is just going to be our years times 12. Which we specified there. And then we've got our different mortgages, which we've actually stored as a list. This is a list of objects. Morts equals fixed 1, fixed 2, and 2-rate. Where fixed 1 is an instance of the fixed mortgage subclass. Our fixed 2 is an instance of the fixed with points subclass. And 2-rate is an instance of the 2-rate subclass. Okay, so for each month, and then for each of these 3 types of mortgages, we're going to make a payment. And again, the way you make that payment is specified by the inner workings of whatever class you're calling here. So when I call and I apply this method, it's going to operate slightly differently because each of these mortgages have slightly different attributes. You should probably go back and look at the other code cell to see how that's really implemented. All right, so we do that. And then for M and morts, we're going to go ahead and print the attribute. That's our legend. And then we're going to go ahead and print what our total number of payments was. So let's go ahead and run this. And And first, I'll start off with a high interest rate. Mortgage rates haven't been like this for years, but they used to be. They used to be actually very high. I've heard that I think maybe even the 80s or 90s, mortgages were closer to 10%, which is almost a credit card payment. But either way, let's suppose you take out a $200,000 loan on a house for a 30-year mortgage with a fixed rate, 0.07. You can compare this with a mortgage with points, where you take out 3.25 points, and then the rate when you buy that number of points is only going to be 5%. And then we're going to compare this with the third mortgage, the one with the teaser rate, one that starts even lower than 7 or 5, but in fact is 4.5%. That's 0.045. But that rate only is valid for the first 4 years. Afterwards, it jacks back up to a 9.5%. So you can already see the output here because I've run the cell. Let me go ahead and run it again. So for a fixed rate 7% mortgage, the total amount you'll pay over the 30 years is $479,000. Sounds like a lot, even though you only took out $200,000. Now, by contrast, if you have a 5% rate, which you're able to buy using 3.25 points, you only end up paying $393,000. So that shows that by anteing up a little bit more, you got access to a lower interest rate, and therefore your total payments were less. And finally, we've got our teaser rates for 48 months, then 9.5%. That's the highest of all, even though it looked really attractive, because in the first 4 years, you had lower payments than any of the other mortgages. But part of the problem was that you were basically thinking too short term, and in the long term was actually worse. So I encourage you to go ahead and maybe Google around and see what are more realistic rates. I think you can get things closer to 4.5%. And maybe with this teaser rate, you can get down to a 0.35. And then maybe we can even have variable rates where it's a 2.5%, but then goes up to, I don't know, 6%. Let's see what that would do. So some of the differences, again, notice all in all, you end up paying a lot less over time. So this is why sometimes people really want to try to capitalize when rates are low by buying a house if they're able to. And so in this case, 364, but again, our fixed with points came out less. And again, our teaser rate, even though we had a full 2% difference for the first 4 years, we ended up paying more in the long run. All right, so I encourage you to play around with that. And in this first in-class exercise, I want you to go ahead and create 2 instances of these mortgage subclasses. One that's fixed rate, 5% loan for 30 years, and then another one that's our 2 rate or teaser mortgage, where we have a 3.5% for 5 years and then 7% for the remaining 25. And just to make sure that you understand how all these methods and attributes are stored, I want you to tell me how much is owed on each loan after 5, 10, 15, and 20 years. Again, how much is owed, not how much you paid. So you'll see what's left. All right, so maybe take a moment to go ahead and do that now. All right, continuing. Of course, all these things are really hard to wrap your head around. And that's because we as humans, we're very visual creatures. And so being able to just look at plots is so much more useful. Now, in contrast to our book, which I call the MIT book, like Guttag, we're not going to use pyplot. And indeed, if you look online, you'll see that the pylab.plot, which is recommended here, if you look up the current data around this, they actually have encouraged people to stop using this Python class because matplotlib is the gold standard. So this is where we're going to have to hop to some other resources. And one of the reasons why I like the fact that we've got Vanderplas, whose text is freely available on GitHub. And so here, this is our Python Data Science Handbook. Again, a very useful book. Looking around if I have my physical copy here. But either way, you've got a virtual copy here. And essentially, this brings all the wonderful features of MATLAB's plotting libraries to Python. And so this is going to be the way in which you're going to move through your our plotting classes. So ideally, all these things are already installed on our server. And according to what I've checked, it appears to be that way. The command for bringing in each of these different classes is using import. So we're importing from existing Python libraries, bringing them into our Jupyter notebook so that we can use them. And there are all these different attributes. And notice that once we've started importing from other libraries, we're going to start using the same dot notation that we use with object-oriented programming. That's because, in a sense, all we're doing when we're importing something like matplotlib is we're telling your Jupyter notebook to go ahead and scope and look at a class of objects which have all these different methods and attributes available to them. And so essentially, we're getting to use already built-in object-oriented programming classes that a bunch of other people have coded. And so we're going to now benefit from instead of writing our own. All right, so we're also going to start using NumPy, which we're going to go over in more detail by next lecture. So these are two instances of sort of libraries or packages which exist within Python 3. And that just by typing import, we're able to bring them in and make access of their methods, make use of their methods. So let's see how we do that. So because you're going to be using these library names a lot, it's very useful to come up with a shorthand for how to refer to them. So for matplotlib.pyplot, we're going to import that under this sort of pseudonym or handle, PLT. PLT is short for plot. Now again, we didn't have to do this but it's just a regularly accepted convention that you'll do that. And similarly, because we're going to use NumPy so much, we don't want to type out the full 5 characters of NUMPY. We're just going to instead use the 2 characters NP. So anywhere where you see NP or PLT, all this is it's sort of the nickname for either NumPy or matplotlib.pyplot. Of course, it's so much easier just to write PLT instead of matplotlib.pyplot every time. All right, so let's see how this works. So I've imported these packages. And so much like what we have with the range function, we now have access to something called Linspace. Linspace is, unlike the range function, capable of taking decimal steps. So what this is going to happen here is that we're going to go from 0 to 10 in steps of 100. Just like with the range function, we have our start, our stop, and our step size. All right, and so let's go ahead and talk through a little bit more of what's going on here. So notice that you want to think of this almost exactly as creating an instance of one of these classes. So X equals a NumPy object, where we've further specified what kind of NumPy object. It's a Linspace object. And then similarly, we're going to create a figure, which we're going to call fig. That's just whatever variable name we want. We could have made this my fig. That's fine. And this is going to be an instance of the plot class. And in particular, it's going to be a figure object. And so we're now going to be able to manipulate these objects by doing things like plotting. And we're going to start getting to use some of these familiar functions from math. Here's our sine of x, which didn't exist as a built-in function inside of Python, but does exist inside of NumPy. Similarly, we have cosine. And then also we've got sine x plus cosine x. So notice that when we do these plots, if we want to kind of suppress some of the internal output, you can always silence them by putting a semicolon. All right, so let's go ahead and execute this code cell and see what happens. Wow, we finally get to look with our eyes at some of these equations instead of just staring at arrays and figuring out how they're populated. And notice that matplotlib is incredibly intelligent. It automatically makes choices of colors for you so that things are visually well separated. So if we wanted to figure out, all right, well, what's which one of these guys is sine? Notice that starts with the blue curve because sine of 0 is 0. And then the second curve we plotted was cosine, which starts at 1. and it's now oscillating values higher than we expect. So it actually goes up. Oh, no, my apologies. It's the orange curve, cosine. Yeah, I knew something was wrong because mathematically, neither sine nor cosine can exceed the value 1. And then, of course, the sum can, but they're out of phase. So as cosine's decreasing and sine is increasing, so they kind of peak here at this one intersection point, then it keeps decreasing, and so on and so forth. All right, so let's go ahead and play around with this code cell a little bit more. I want to print the type of x. See if this works. So notice that our Linspace object, we're told is an instance of this class of numpy.indArray. And so we can also do things like, what is the type of fig? Remember, fig is our figure. And so again, Python tells us that these are instances of an indArray numpy, and this is an instance of a figure in matplotlib. All right, so we can suppress these outputs for now, but now we're getting to actually play around with how we can modify some of these attributes here. So I encourage you to go through and maybe play around with and read this section of van der Plas, so you can see how we treat some of these objects. And you can see here we've run essentially the same example here. And they give differences between IPython shell and the notebook. Again, we're using a Jupyter notebook, so that's sort of the one we're going to do. Notice here we can figure out other ways of modifying attributes. And these attributes have set values or default values. Remember, those are values which you don't need to pass as an argument because it just assumes you want things to be sort of steady. But if suppose I wanted to have a dashed line, I could just do that by manipulating this, bringing it over, and let me go ahead and just do it here. So by doing that dash dash, I've changed the display type. Part of what you need to do now is just get into matplotlib and see the various attributes that you can play around with. All right. So it's important to realize that, again, everything in a computer basically has to be represented as something like an array. You know, we can't handle actually continuously varying objects because we just don't know how to represent that computationally. And one way in which you can really see this is that before we had x as np linspace 0, 10, 100. That meant went from 0 to 10 with 100 steps. So, you know, I had a small step that occurred at every 0.1. Now I can change that and I can be a little choppier and just say, I'm gonna go from 0 to 10 with 10 steps. So that means that I'm gonna end up having only a value essentially at every integer. And so again, matplotlib is wonderfully intelligent and knows like, oh, I'm just gonna connect the dots and try to make this look as pretty as possible. So this is our underlying grid. We now call Y just to keep things separate from the previous code cell. And again, now we create a separate figure, figure 2, which is going to be, we call it as a figure object. We don't supply any arguments right now. And then I'm going to go ahead and do exactly what I just did, where I want to think of this as the X coordinate, and that's why we call it X in the last slide. And then now what I'm going to do is for each entry in that array, in this case it's Y, which is just a linear separated sequence of decimals from 0 to 10, steps of size 1. I'm going to take sine of that value. And just to make the plot different, I'm going to go ahead and use my original solid line, my dashed line, and then here I'm going to use my sort of dotted line, which is indicated using this little quotation marks and then the semicolon. All right, so let's make sure that all works. So it all seems to work just fine. And you'll see how much choppier this function is. And of course, if I change this to then go, let's call it 50, suddenly looks so much smoother. Again, let's do 10 for comparison, 20. Still see some little steps here, but by the time we get up to 50, it's almost indiscernible. You can still see it's a little rough, but either way, go ahead and play with this. I'm going to return it to its original value. All right, so one thing that's going to be really useful, especially as you get to your final reports, is that once you have some output that you want to save and include into a PDF document, there's a built-in method for that, and that's called savefig, where you can go ahead and supply the file name. And if you run this cell, it's going to go ahead and store in the computer a file by that name. Or in your case, it's going to populate your folder on your Jupyter Hub server with a figure by the name of my first figure. All right, so let's try to tie the two things we just discussed, mortgages and plotting. So let's start off really small and assume that we only have a $10,000 initial investment, but we're going to assume that we get an interest rate of, let's say, 5% every year. How does that grow? Well, if we really want to understand that and the sort of underpinnings, we could start by creating an empty list, and then we're going to go for I and range it years plus 1, because again, this always ends at whatever this entry is here minus 1. So if we wanted to end at our final year, it's that year. And then we're just going to append principal, and then I'm going to add to my principal. So that's what that plus equals does. Principal times the interest rate. So here I'm thinking of this as an annual interest rate. I'm assuming that I've maybe invested this in a mutual fund or a stock, which is reliably giving us 5% return every year. And I never take any money out. I just keep it in the market, never mess with it. So one thing that's nice is that you can still work with ordinary lists with matplotlib. NumPy is just really optimized for doing some of these scientific computations with functions like sine and cosine, but it also knows what to do with lists. All right, so let's see how this works. So values, we initiate as an empty list, and we append a principal, where that principal is increasing by whatever the principal was in the last year, where I've then augmented by my interest rate. All right, so I create my figure object, fig, and then I now invoke all these methods from the plot class, which is really matplotlib. And I tell it to plot the values. And I get to modify some of these attributes of my plotting object, like its title, just by feeding it a string. Whoops, don't want to do that. And then I can also modify the X label, X-axis label, and the Y-axis label. And then by looking at the last entry, I can see how much a $10,000 investment, if invested for 20 years, how much that's worth. You can see here that if you can put $10,000 into an account that earns 5% annual interest, then after 20 years, that $10,000 more than doubles. It's worth $26,532. This is the fundamental assumption around retirement. So you start putting in money now, and then that's going to go into a retirement account, which hopefully earns reasonable percent interest, so that then when you go to retire, it's worth 2 or 3 times as much as you put in. Say you only need $30,000 a year to live on when you're retired, then you want to have at least put in $10,000 a year for a little bit longer, but we'll see how to calculate that in our live exercises. All right, so we're going to do a few more things with our mortgage class. We're almost done. Okay, so again, I've just completely copied over the original mortgage class, and we had make payment, get total paid, but now we also have methods that integrate with matplotlib, which allow us to plot our payments, plot our balance, plot total paid, and then we can look at the net cost, so plot an approximation of the total cost of the mortgage over time by applying the cash expended minus the equity acquired by paying off part of the loan. So this, again, to read the comments, equity acquired through payments is the amount of the original loan paid to date minus what's still owed. So this sort of operates under the assumption that your house doesn't really increase that much in value, but you get to essentially own more and more of your actual house as you make payments off of that. So that then at the end of your mortgage period, say 30 years, you now have a wealth which is equal to the amount you loaned, hopefully more, assuming your house actually acquired value over that period of time. All right, so we're going to see how all these different methods that we just added to the mortgage class can be used. I'm going to hit Shift Return. We're going to store that into memory. Again, I got the same mortgage subclasses that I already specified. So now I've written a large function called plot mortgages. Again, it looks like a lot, but all you're doing is basically making a plot, giving a title, giving an x-axis label, giving a y-axis label, and then we're also going to look at the cost of that, the balance, and the net cost, which essentially can tell us our equity. Now we're going to iterate over all the different mortgages. So the function assumes we're given a list of mortgages and a total amount. And again, when you specify each of these mortgage objects, you have to specify like, what are the rates and what's the loan period. All right, so now we've got this lengthy function, and I encourage you to try to read this code in detail. And then we're going to go ahead and compare our mortgages, just like we did before, but this time we're going to use pictures. So hit Shift Enter to bring this into memory. Let's go ahead and run this. So for a $200,000 loan amount, 30-year mortgage, say a fixed rate with 7%. Again, luckily rates are much lower right now. Versus a mortgage with points, 3.25, 5%. And then we also have our 2-rate mortgage. So what happens in our first plot here is we've actually brought in a legend, which indexes what each of these curves are telling you. This is a great example of good visual displays of quantitative information. So for our first 48 months with our teaser rate, we end up having the lowest monthly payment. Notice you're only paying about $1,000 a month. So that's pretty impressive because it's competitive with rent, but now you're actually getting to own a house and you get to do what you want with it. Versus, for our fixed 7%, we've always got a mortgage that's sitting above $1,300, maybe not quite $1,350. Versus if we were to use the point with the lower percentage rate, also lower principal, again, we're just paying a shade under $1,100 every month for property that we're hopefully building equity in, meaning we're acquiring wealth. All right, so in each of these plots, we look at how much cash you're putting out. So you can see here, and if you're able to zoom in, that teaser rate is 4.5. You start off by paying out less cash, but over time, around this looks like 120 months, so maybe after 10 years, your cash outlay, the amount of cash you have to put into your house, so much more. And you notice that again, for a $200,000 loan, you're going to be outlaying over $500,000. All right, so then we've got these other curves here, which look a little more reasonable. All right, so now we've got our balance. So this is the really depressing thing about having a house. For the first several years, you essentially have still a lot left on your loan. And the reason for that is that you're essentially paying off interest from the future now without actually paying off principal. So even though you take out initially 200,000, you can make well over between 1,000 and in some cases up to $1,600 a month payment. So over the course of a year, you've already paid out more than $12,000. You still haven't actually changed that much of your balance. And indeed, after 3 or 4 or 5 years, you've paid in $60,000. But notice your principal hasn't dropped $60,000. It's because you're largely paying off interest. This is also why you don't want to buy a house unless you're able to sit on it for a while and eventually get that balance down, so that then when you can sell it, maybe 10 or 20 years out, you now actually get to capitalize on that difference. And all of that is expressed in some of this last last graph, which sort of tells your payments minus your equity. And so here you get to sort of see what's the actual kind of cost of having a mortgage versus if someone could just buy you a house outright. So notice again, this value here, this $350,000. What that is assuming you've acquired now $200,000 value in the house, but you paid out again up here over $500,000. So the cost difference, 500,000 minus 200,000 is that 350. So this is again why if you can get these lower interest rates, what a house ends up costing you in the long run isn't less. But again, the nice thing is at the end of the day, you should have this large amount of wealth. And historically, Americans have built wealth by having houses and being able to pass on houses, which is also one of the reasons why the 2008 crisis was so devastating, because a lot of people lost their houses and consequently the wealth that they were trying to build up for themselves and their kids. All right, so that's it for today. So I want you to go ahead and navigate to this section of Van der Plas, where you look at sort of simple line plots and sort of mess around with some of the various options here. And I want you to modify the compare mortgages function so that the graphs of each mortgage type get a different color. So that means you need to go in here and look up, how do you change the color? Well, here you go, you have it here. You can just literally set a new attribute color, and there are lots of different ways of passing that color, either hex values or some other grayscale value. All right, so go through and make sure each mortgage always gets plotted with a different color so that when you look back at these plots, instead of just having blue with different textures, you'll have different colors like orange, blue, green. All right, so once you've done that, I want you to modify the loan and rates amount. So I want you to just play around and see how can you modify the loan and rate and teaser periods to make these graphs very, very different. So imagine maybe you got a 0% down, but then you have to 0% interest for 48 months. Go ahead and try this. All right, so that's it for today. I look forward to seeing you in class.